Hi students, now we'll talk about how to derive formula for confidence interval for the population mean mu. We have discussed that when we draw the sample size of n, we use z as a sampling distribution for the sample mean with this structure. Okay, and then later on we have transformed and substituted the verifications of mu of x bar equals to mu. So in place of mu of x bar, we can substitute mu, and in place of sigma of x bar, we can substitute sigma divided by root n. Now, what is confidence interval? Confidence interval is selecting or choosing certain percentage of area under the curve that is strictly a central area. Now we know that unknown population mean mu lies in the center, and would like to estimate this with the help of confidence interval. Let's assume that the total area that we have selected in the center is 1 minus alpha. So from the total probability of 1 that is representing the entire curve, we have taken away alpha part. So whatever area we have taken away from 1 should be equally assigned and allocated to the tail end regions. So this is how we can assign alpha by 2 here and alpha by 2 here. Now, we know that when we are going to write down the central value in z terms, z is equal to 0 is a value that is representing center. And left hand part will represent negative values of z, whereas right hand part under the curve will represent or incorporate positive values of z. Now, what if we will write down the lower bound of z as minus z alpha by 2 and upper bound as z alpha by 2? Here, the subscript of alpha by 2 are indicating the areas below the lower bound of z, what we have indicated here, and above the upper bound of z, what we have indicated here. Probability is representing the area, and over here we can see that the area covered or bounded between minus z alpha by 2 and plus z alpha by 2 is 1 minus alpha. So in probability terms, what we can do, we can write down the area selected between the lower bound and the upper bound of z values as 1 minus alpha. So we can say or state that probability that z lies between minus z alpha by 2 and plus z alpha by 2 covers the area of 1 minus alpha. Now considering only this central part, what we define as the limits for z, we will pick this, rewrite it down again. Now we know that z over here we are using as a sampling distribution of x bar, for which I have written down the formula over here. Now what we can do, we can substitute the formula of z in place of z. Now what we need to do in the next step, we would like to construct the confidence interval formula for mu. So we need only mu to be isolated or left alone in the center, rest of the things must be moved. So if something is written in fraction, we prefer to move the denominator first. So denominator contains or is the ratio of sigma divided by root n. So if we multiply entire inequality by sigma divided by root n factor, this is how we can get this factor removed from the center, and this would become the part of lower bound as well as upper bound. Now in the next step, what we do, we have to remove this x bar factor from the center, and we will make use of the concept of additive inverse for this purpose. So getting x bar subtracting throughout this inequality, we can get it removed from the center. So this is how we can write down this step of removing x bar from the center. Now we need to remove in the end this minus sign that is linked with mu attached to mu. So when we multiply this inequality from minus sign throughout minus 1 throughout, we can get the negative sign removed from the center. So multiplying this left hand side or the lower bound of this inequality by a minus 1 factor will change its sign, and this will become x bar plus z alpha by 2 times sigma divided by root n. Mu I am going to write down in the center, removing the negative sign attached to it, and this right hand side inequality component will become, the first term will become positive and the second term will become negative. So x bar take away z alpha by 2 sigma times divided by square root n. Now as we know that whenever we multiply inequality by minus 1 factor, inequality signs are inverted. Let's take an example with some numeric values. If minus 3 is a value less than 2, when we multiply both the parts of inequality or both the numbers by minus 1, so this will become plus 3 and this would become minus 2. Now inequality will be inverted because the relationship is now altered completely. 3 is a value greater than minus 2. Therefore, we can apply the same rule over here, since in the previous step we have multiplied the entire inequality by minus 1 factor. So consequently, inequality signs have to be inverted. Now to identify the lower bound and upper bound, we need to look at the starting factor on both the bounds. It is x bar. And when we are adding something to x bar, it will represent the upper bound because it gives us a higher value. Similarly, if we look at the right hand side or the upper bound currently written, so that's not the upper bound in fact, because we are getting some factors subtracted from here. So whatever we are, where we are subtracting and where we are adding should be written as the lower and upper bounds respectively. So we will again invert the inequality. We keep mu in the center, but in the lower bound we need to write down x bar minus z alpha by 2 times square root sigma divided by square root n. Similarly, we have to write down x bar plus z alpha by 2 times sigma divided by root n. So this is how we get the formula for confidence interval of population mean, and specifically we call it 1 minus alpha percent. This is the formula for 1 minus alpha percent. confidence interval, this is what CI stands for the population mean mu. We can use this formula to determine the unknown value of the population mean mu for any given data. What we need to have to apply this formula, we need to have sample size with us. We need to have either computed values of mean with us, or must be given a data from which we can compute x bar values. Furthermore, we need to have sigma or population standard deviation value given in advance that we can borrow from the prior information. We also substitute the z value depending upon the confidence interval percentage with which we are asked to construct this confidence interval. So now we will try to come up with 5 commonly used confidence intervals for population mean mu based upon z distribution. And for this reason, I'm going to open z table because we need to have it. We will consult the z table for every value of z. Now I am over here making a table for the 5 commonly used confidence interval percentages. Starting with 80%, 90%, 95%, 98%, and 99%. Here we write down z alpha by 2 value, and in absolute terms we will completely ignore the signs. Now for 80% CI we need to draw the curve. We will indicate middle 80% area under the curve. If we are keeping 80% in the center, then we need to allocate or assign 10% and 10% areas in the lower and upper bounds. So 10% transforming it to decimal numbers, it is 0.10, and this is also 0.10. Now we go to the z table, try to get the z value located corresponding to 0.10 probability, and now you can see when we go for minus 1.2 rho, this is the nearest possible probability that is available in the z table, which is very closer to, in fact rather closest to zero point 0.1 target value, because if we look at the other neighborhood value that has a deficiency of 0.0015 units, but this is exceeding only 0.0003 units, therefore this value is acceptable for us. But we are interested in location probability we have located, but we need to locate the z value at which this particular probability is located. So this is the 8th column. Consequently, minus 1.28 would be the value of z. So if minus 1.28 is the value of for the lower bound, plus 1.28 would be the value for the upper bound. Why? Because 0 exists in the center of the bell-shaped curve if we refer this bell-shaped curve for z distribution. So we can say, ignoring the signs, because we are writing it down in absolute terms. So ignoring the signs of plus and minus, we can code this value as 1.28. Now, moving to 90% CI, taking 90% central part, we need to allocate the remaining 10% probability equally on the left tail and right tail part. Now this time we need to consider this 0.05 probability to get the z value from the table located. Now if you focus on 0.05, this is the row in which you can find two probabilities that are equally closer to the target probability. Target probability is 0.05. 0.0495 is 0.0005 units below the target probability. Similarly, 0.0505 is 0.0005 units above. So in this case, both the neighborhood values are at the equal distance from our target probability of 0.05. So what we can do, we can read the location of these two probabilities in z terms. So that's minus 1.6 and 4 and minus 1.65. So minus 1.64 and minus 1.65. We go for the average of the two values. Average of minus 1.64 and minus 1.65 is minus 1.645. Therefore, minus 1.645 here plus 1.645 here, we quote the z values without signs in absolute terms for 90% CI. Now, if we go for 95% CI, then in that case, we need to leave 0.025 two equal areas under the two tail end regions. Now, if we consider this 0.025 probability, we need to go to the table again. 0.025 probability is the only probability that is available exactly in the z table. You can see this is given in no point no 25 here, in minus 1.9 row and 0.06 column. So minus 1.96 is the value of z corresponding to this probability. Therefore, 1.96 is the value that we substitute here.